What will be e power I theta plus e power minus I theta by 2? Cos theta, right? So the first term is cos theta. If I pull out a minus I, it will be e power I theta minus e power minus I theta. I have a minus I. If I take it to the denominator, it will become I. So e power I theta minus e power minus I theta by 2I is sin theta. So this is equal to sin theta. And this one, I pull out an I, this becomes minus sin theta. And then this is cos theta. Okay, so this is a kind of a rotation matrix. This is a rotation matrix. If you have a coordinate system, xy, let's say you have a vector which can be written as x and y. Correct? If you have a coordinate system xy, you can say that you have a vector with respect to which you call this as x and y. Now suppose I rotate this coordinate system. I have got an opportunity to use some color chart. So let's say that I have got a coordinate system which is rotated like this. With respect to the previous coordinate system, this is my x prime and this is y prime. So this angle, I call it as theta. Now you can ask the question, what is the transformation? The coordinate system is rotated from xy coordinates to the x prime y prime coordinates. So the same point with respect to this x prime y prime is denoted as, so with respect to xy it is x comma y, and with respect to x prime y prime we will call this as x prime y prime. So the same vector, the vector r, can be written as x times I plus y times j, where I and j are unit vectors in the xy coordinate system. But the same r can also be written as x prime times I prime plus y prime times j. But now you ask the question, what is I prime and j prime? So I prime can be written as I prime dot I into I plus I prime dot j into j. So if this is your I prime dot I is cos theta and I prime dot j is sin theta. Correct? Because this is theta, this is 90 minus theta. So this will be equal to cos theta times I plus sin theta times j. Similarly, I asked what is j prime. J prime is j prime dot I into I plus j prime dot j into j. J prime dot I, j prime is here, I is here. J prime to I prime is 90, this is 90 plus theta. So 90 plus theta is minus sin theta into I plus j prime dot j. If this is theta, this is also theta. So this is cos theta times j. So if you now look at this transformation axis, I prime, j prime can be written as cos theta, sin theta, minus sin theta, cos theta into ij. So this matrix is exactly the coordinate rotation matrix. The transformation matrix from I to j, ij to I prime j prime, the coordinate axis is rotated, is given by this matrix. So the sigma 2 matrix, which actually even gives you infinitesimal rotations. This is called the generator of rotations on a plane. Okay, so this is the reason why you call sigma 2 as generator. We will study this in detail in group theory. The generator of rotations on a plane. This is also called generator of elements of the group SO2. So SO2 group is the set of all rotational matrices with fixed with the determinant positive, with the determinant 1. So the sigma 2 generates all the elements. So this is essentially called the generator of SO2.
You mentioned that sigma 2 represents infinitesimal rotation.
Yes. So you can say that if you consider this theta to be very, very small, in that expansion, so let's say this is your r of theta. Okay, so you can write here. So let's say that you have r of theta is equal to 1 plus I sigma 2 into theta, and forget about all other quantities because theta is small. Now you can ask the question that what is r of 0? That is identity. Correct? So r of, if you can call it as delta theta, is equal to identity plus I sigma 2 into this delta theta. The other things can be forgotten. So the change r of delta theta minus, I can call this as r of 0, is equal to I times sigma 2 delta theta. So if you want to call this in this language, I take it to the denominator here, and this is the infinitesimal rotation from the identity is governed by only this sigma 2.
I.
Yeah, so I is there, but this is because sigma 2 is complex matrix. Okay, so if you have I times sigma 2, it becomes a real matrix. I can always choose the real matrix as a rotation. So this is in some sense the rotation matrix and the generation of rotation matrices. You will see that three-dimensional rotations in rigid body dynamics and classical mechanics is related to this, but there, since you have three-dimensional rotations, you have three independent rotations.
Actually, we don't talk about the internal structure of the generator, just the
Internal structure.
what is the nature of that matrix. Sigma 2 is also a matrix.
Sigma 2 is a matrix.
What is it made up of? What is the structure of that matrix?
As far as rotations on plane is concerned, there is only one generator because this is one parameter, theta is. But if you look at three-dimensional rotations, that is instead of SO2, if you consider three-dimensional rotations, there we require three generators and three angles. You know, Euler angles are the three angular degrees of freedom. Corresponding to each angle, you will have a generator. And that generator will satisfy the same algebra that angular momentum operators satisfy in quantum mechanics. So essentially, they satisfy the same commutation conditions. So angular momentum matrices are the same angular momentum matrices in orbital angular momentum matrices are 3x3 matrices. There will be three such matrices which will generate a general rotation matrix in 3 dimensions. You can equivalently describe by using Euler angles or also using an arbitrary rotation in 3-dimensional space can be visualized as a unit vector specified and then a rotation by an angle about that vector. So a unit vector specified should have n1, n2, n3 direction cosines of the vector, but there will be two independent because n1 square plus n2 square plus n3 square is equal theta. So there are 3 degrees of freedom. Similarly, if you take Euler angles, there are 3 angles, theta, phi and psi. Those are 3 degrees of freedom. These two are equivalent distributions. So one can describe it using Euler angles, or you can describe it using, it is called axis angle parameters. Axis angle parameters or Euler angle parameters are equivalent. You can go from one distribution to the other.
Lorentz transformation is also a rotation like this.
Lorentz transformation is not a rotation in this sense, because it's a rotation in, you can visualize that as a rotation in what is called an Minkowski space. So there you have 3 axes which are real and 1 axis that is imaginary. So in that, yes, it's like a rotation. Because the Lorentz metric, the Lorentz transformations do not leave the dimension of the vector invariant, except if you define that I times Ct as the 4th axis. Then you can say, you can interpret, that is called Minkowski space. And in that space, you can say that it is like a rotation. Okay. So this is another exercise where we can